بسم الله الرحمن الرحيم. اللهم علمنا بما ينفعنا وانفعنا بما علمتنا إنك العليم الحكيم. السلام عليكم ورحمة الله تعالى وبركاته. Hello everyone, I hope you are doing well. Today I will present to you all my license project, which is an AIoT-based quality control production line. For those who don't know me, I'm Mohammed Yunus from Algeria, a third year automation and control system engineering student at the Faculty of Technology, University of Boumerdaz, Electro Scientific Lab President, and the project manager at Mamin Scientific Lab. Here is the outline of my presentation, where we will discover every single detail of this project. Well, I usually start my presentations with a problem, and the problem we will talk about today is the edge computing. Edge computing technology nowadays plays an important role in the fourth industrial revolution that converges data processing effectively and quickly close to the source. At the same time, edge computing could be an issue when we talk about security, big data, incomplete data, maintenance costs, and especially the infrastructure investment. Moreover, cloud computing plays a significant role in the Industry 4.0. Cloud computing is the delivery of computing services, including servers, storage, databases, networking, etc. So the solution for the edge computing problems is the cloud computing. In this project, I used many technologies. So when we talk about big data, AI comes, or artificial intelligence. And while we are working on cloud, the IoT is present, or the Internet of Things. And if we mix them together, we will have AIoT, or artificial intelligence of things. The hardware used for this project are the Json Nano Dev Kit from NVIDIA and NCS, which is the Neural Compute Stick 2 from Intel. And these two kits are used for the AI training. I used also the Raspberry Pi, which is going to be our server, STM32 Nucleo board for embedded systems and controlling the production line, ESP32CAM for image processing, and ESP01 for data transmission. Software design section is divided into 4 subsections: artificial intelligence, software development, embedded systems, and design tools. For the training, I used TensorFlow, which is an open source framework from Google. I used also Keras API with CNN algorithm or convolutional neural network with AlexNet architecture. For the phone app, I used Android Studio with Flutter framework, which works with Dart as programming language. Flutter is also an open source project from Google. For the web development, I used VS Code or Visual Studio Code as the IDE, which is an open source integrated development environment from Microsoft. And of course, I used HTML, CSS, JavaScript for the front end, MySQL, and Node.js for the backend. For the desktop app, I used Processing 3, which is an open source project from MIT that uses Java as programming language. For the embedded software, I use STM32 toolchain that contains tons of environments and tools. For this project, I used STM32CubeMX for pins, protocols, and clock configurations, STM32Cube IDE for programming the microcontrollers, STM32Cube Programmer for flashing the framework, and lastly, STM32 monitoring for debugging and monitoring the data. The tools used for developing the ESP boards are Platform.io with ESP-IDF. Platform.io is an extension used with Visual Studio Code, and the ESP-IDF is the official integrated development framework from ESP Receive. For the Raspberry Pi, I used Raspbian as OS or operating system. I use SolidWorks for 3D design, Prusa Slicer for 3D printing, and Altium Designer for printed circuit board or PCB design. Well, here is the software and hardware implementation. As I said, we trained the machine with Jitson Nano and NCS2, and we put our model on the server, which is the Raspberry Pi. The production line sends the image to the server, and then the server classifies and send back the result to the production line. At the same time, the production line stores all the data on the database in order to display the analytics on the dashboard. After the implementation, I had the 83% as training accuracy, and this is quite good for us. Here is the 3D design and the final look after the printing the parts and assembling them. This is the web-based real-time dashboard, and this is the final printed circuit board that based on the ESP32 and STM32F411 chip. It has also an Ethernet connector with different drivers and it's ready for produce. Well, we have the demonstration video.
Hello people, so this is my license project and here is the production line with the robotic arm controlled by the STM32 Nucleo board. And here we have the ESP32 cam. For the other parts we have the server based on the Raspberry Pi, cooling fan, carbion, and the Ethernet cable for the SSH communication. So this production line classifies the pictures of the gears. So how it happened? The ESP32 cam takes the picture and then send it to the server classify and then turn back the data and or the result to the ESP, and then the production line put the gears into classes. So this class is for, I guess, for good gear, I guess. And this is for the defected one. And if we come here, we see this button, and if we push it, we see this production is open, and we have here some random pictures of gear. So this one is a good one. Place it here, stop a while, and so it took the picture, send it to the server, and then put it into the class. So we have here a defected one. Put it here. Send the data. And then turn it back. We have another one. This is a good one. Put it here. And here it is. And here we are with Electro Scientific Lab. It messed up, I know.
So this was a small demo. Of course, I faced some problems during implementing this project. First, the Raspberry Pi got very hot when processing the data, so I placed a cooling fan. Second problem, the model makes mistakes sometimes when classifying. For example, it recognizes the defective gear as a good gear. So I need to collect more data and rechain it again with another platform, or maybe changing the architecture used. Last problem, the production line takes a long time between sending the image and receiving the result. So I need to connect the production line with the 5th generation network, or 5G. In conclusion, this project aims to inspire a new artificial intelligence of things, IoT-based quality control production line that enables a series of enhancements in production management. Our future work. So I want to build a high performance computer, or HPC, that based on the FPGAs, or field programmable gate array. So the FPGAs are the clients. We connected them to one server with optic fiber, and we will implement the quantum machine learning algorithm on it. And this is going to be the 5th industrial revolution. So all the ideas for this project started from this piece of paper that I drew it when I was traveling with the chain. Last but not least, and while all the frameworks, libraries, and tools I used in this project are open source except the SolidWorks and Atom Designer software, I want to open source in this project in order to let you to contribute or develop it no matter where in the world you live. I leave the GitHub profile link, so check it out. Finally, I want to thank everyone who listened to this presentation. I hope you enjoyed this video. If you love it, hit the like button. If you want to see more projects like this, hit the subscribe button. Please leave your feedback in the comment section. Thank you very much. See you soon and take care.